Hi guys and welcome to this Hi guys and welcome to this CP2 overview. My name's Amos and this is the topic on environmental impact on larger buildings. So we're just going to look at understanding the impacts of these environments and why certain materials and technologies are used in larger buildings. So the first thing to look at is rain and moisture. The rainfall intensity and how this can affect the building at both low and high intensities. For example, low intensity is considered normal rainfall, and an acceptable response to this is to design flashings, drain joints and roof overhangs and gutters and more. High intensity creates increased load on stormwater systems and flash floodings. So a building's geographical location has significant effect on its exposure to rainwater and moisture. And the Building Code Clause E1 surface water provides detail on the expected rainfall intensities throughout the country. An example would be that a building in a zone with high rainfall intensity creates a greater drainage demand for roof surfaces. Modern commercial buildings commonly use internal gutters which can overflow and allow water into a building if the internal gutters aren't of sufficient capacity. And water ingress into a building's cladding system can obviously jeopardise the integrity of a building's structure due to the corrosion and the rot. New Zealand is divided into a range of wind zones, ranging from low to very high. As you know, a high wind zone requires a high capacity to resist those lateral loads imposed on a building. And for commercial buildings, generally a specific design is required by a structural engineer to assess the wind demand and capacity. The way in which wind forces act on a building are complex and they're not necessarily that obvious. For example, wind speed is lower at ground level due to the Earth's friction, or frictional drag if you like, which means it can be faster at the high altitudes on taller buildings. In addition to that, you can see that we've actually got some areas of suction created on the building as well as the wind passes over and then creates these wind eddies around the adjacent side of the building. At a more micro level, wind pressure can force moisture into the building envelope and potentially that can affect the integrity of the weather tightness and of course that can lead to potential structural issues. So we come back once again to structure. Corrosion and durability is something else we're going to be looking at with this topic. New Zealand is divided into 3 exposure zones depending on the severity of the exposure to wind-driven sea salts. So buildings outside the scope require specific engineering design. You can see on this map here from 3604 that the different shaded areas relate to the zone that it's in. So the white zone is the most severe, and as you get further inland the zones become less severe, except for these geothermal areas where there is quite a high corrosive component due to the sulphur. So we're talking about areas like Rotorua and Taupo. The New Zealand Building Code Clause B2, durability, is also an important compliance document which sets out the minimum durability of all building elements in terms of years. Table 1 shows us that wall framing for timber or steel which is load bearing, requires 50-year durability. So one of the things we'll be looking at is making sure we understand the durability life requirements of those structural elements. We'll also be taking a look at snow loading. And snow loads on roofs, they vary relative to the geographical location. And the loads from the snow can add significant load to a building structure, and we'll look at ways a building can withstand these loads by structural design and roof shape. This map here shows the snow zones from NZS 3604. Solar effects, something else we'll be looking at. This subtopic looks at the impact of solar gain on a building in terms of the effects of heat buildup, sunlight and shade, and what strategies we can use to mitigate the impact of these effects on the building. Excessive solar gain within a building can create a high demand on the HVAC systems in an effort to equalise the internal temperature. So these systems have to work quite hard to reduce those temperatures in the height of summer, for example. We get a lot of heat gain in through the north facing side of a building, And a simple passive solution to reducing heat gain in a building is to create a roof overhang, or an apron to the building facade. So here's a couple of examples here, just showing a big overhang, which can give us some sun shading. There are other simple passive solutions, and we'll explore these in the lecture, of some passive design that utilises overhangs to produce shading within the building. Hey, look, thanks for watching this quick overview, and we'll cover this topic in more detail within the lecture session. See you later.